Okay, so our speaker today is Bernardo Uribe from the University of Barranquilla, Colombia, la Universidad del Norte, better. So his title is, you can see there, Axion, Insulators, and their Topological Invariants. Please, Bernardo, go ahead.
Well, Guillermo and Guillermo, thank you very much for the invitation. Thank you, everybody, for joining. Guillermo asked me to speak about some recent work that I've been doing with my physicist colleagues here at Uninorte. I'll try to organize all this information in such a way that is somewhat clear to all of you. But mind me that I will talk about many things that are in condensed matter physics that perhaps I'm not the expert on those things. So the idea is I will try to lead you to these materials that are now called Axion insulators and insulators, and I forgot an R in the title. And then you'll see how it relates to these topological invariants that I'm going to talk about. But I'll start on the basic world. So we'll be dealing with crystals, and crystals are materials on which the atoms somehow locate themselves in such a way that they are somewhat repeated in 3 dimensions, and also so that there are symmetries that you can somehow move the crystals around, and the position of the atoms somehow are the same. And these crystals, you see them all over the place. The salt is one of them, but there are many, and they are now very important for properties of conducting materials and to finding superconductors. This has been classified many years ago. So there are 14 types of translational symmetries that crystals may have. These are these 14 lattices that you find on the left, which means that you see the description of the position of the atoms, and then once you move in these 3 different directions that are somehow written on the left-hand side, then you see that the whole crystal looks the same. And there are these are symmetries that translate. On the other hand, we have symmetries that are called point group symmetries. Namely, now you fix just a point, fix a point of the crystal, and then you see what are the symmetries fixing a specific point. And because of the 3D structure of the crystals, there are only 32 point group symmetries. So namely, these are the translational ones and the pointwise symmetries. From the point of view of, as we may see it, is that we have the group of rigid symmetries of the 3-dimensional space, and we put on one side the translation, and the other hand the rotations and inversion, and we take the lattice part, namely the translations on the left-hand side, and the group of symmetries will be a composition of translations and point group ones. But these crystals or the symmetries divide in 2 groups, the ones that are called symorphic and the other ones that are called non-symorphic. Symorphic is that one finds a section from the point groups to the whole group of symmetries, and non-symorphic is that there is no section. And namely that you may have symmetries that are rotate and translate, yeah, like a screw, like 60 degrees rotation and translate 1/2. Then these things are the type of symmetries that are called non-symorphic. So depending on each one, of course, you have different properties. The whole classification of the symmetries for crystal has been already done. It's quite nice. There are some web pages on which you can actually go and click to the group and get precisely all the matrices that define the symmetry group. There are different types of notations with numbers, with letters. Nevertheless, it's somewhat complete now, because you see that there are not that many groups around, and that somehow the crystals may have a symmetry group.
May I ask a question? I mean,
yes.
Right. So you had 14 translation symmetries, but then you said it's Z3. group of translations.
Well, no, I didn't say. Sorry, I said it wrong. There are 14 types of 3D lattices. 14 Bravais lattice, 14.
And then you have 14 translations down.
No, and then not 14 translations, 14 types of symmetries that are translations.
I see. Okay.
So you may count you should think of the symmetries might be moving up, like this one, like the cubic, and all they have the same distances, or it may be that going up is twice moving to the left and to the right, or the three are different, or that is a little tilted to one side, and so it's not a cube but like a monoclinic, as it's written here.
So a lattice always has Z3 symmetry anyhow. Right?
Exactly. Somehow it depends how you embed it into it depends on what lattice, how do you embed it, no? How do you choose the basis?
That's right.
Yeah.
So
this it's just C3 for us, but for the geometry, for the physicists, there are these types of symmetry because you need to recall many things, many angles, many distances. Yeah.
So this would be, it would affect the way on which the orthogonal transformations act. I mean, there is an extent, so it's always C3, but it's a different O of 3 module.
Exactly. So it's always as Guillermo says, it's always C3, but this embedding it's different, and so you're choosing a different basis, and yeah, good. So this is the whole complete group classification, and you choose 14 lattices and 32-point group symmetries, and so going a little bit ahead, then how is this somehow studied? It's studied using something that is called density functional theory. A highly non-trivial physicist discovery or development. So it's how to how to solve or how to study the Schrödinger equation whenever we're going to do it at the atomic level, but so that we can see what happens at our distances. Now somehow we have 10 to the 26, 10 to the 25 atoms, and so how do we solve this sort of equation? But so the standard equation, or this equation we need to solve, is the Schrödinger equation. We have some cinetic term, we have some potential here that is due to the nuclei, and what is highly important here in this setup is the interaction between the different 8 atoms. So, but as you can see, this is supposed to be for each electron, or say each atom that you have, and this is out of our bounds to solve. So the idea is something that is called density functional theory, which is I'm just to put it in just a slide, and this is a.
Sorry, may I have a question?
Yes.
For which n this equation could be solved exactly, not using this density functional theory?
Oh, you're asking me something which I know not much about. N equals, this is very difficult even for small n's. And the whole point is that once you put many n's, then the whole becomes somewhat simpler. But this is solved for whenever it's solved in a computer, you use first neighbors, second neighbors at the most, third neighbors, if that's it, but not the whole neighbors.
You mentioned that n should be interpreted as a number of particles, but also n could be maybe interpreted as the atomic number of a particular atom. Yeah. Yes.
Yes, we need to solve for each electron in some sense. Yeah, so atoms and electrons. So
even for a single atom, already this is complicated.
It is very complicated for just one single atom. Yeah.
Mm-hmm.
Even they cannot solve even the helium case, which has 2 electrons. Yeah.
Even that one is already highly sophisticated.
That's not solvable. That's not integral.
So n equal to 2 is already large in some sense.
Yes.
Okay.
Yeah, absolutely. Yeah.
So again, I'm not at all an expert in density functional theory. I'm just trying to somehow give a glimpse of how our physicist colleagues somehow had tackled this problem. And so after doing this very clever idea of somehow averaging most of the particles besides one, or the electrons, which is this. I'm just giving you a glimpse of an idea. This is a whole theory behind it, no? Then one leaves the equation to be solved just with one free variable, or three, because we are in three-dimensional. And we solve this equation for the electron density. Somehow we just put all these in a density functional. And with a highly non-trivial process that is done in supercomputers, because you need to put a grid and you need to solve this Hamiltonian for all these levels, as we said, and then putting them together, they managed to basically get the density of these energies of this Hamiltonian, and they plot them in such a way that you might see them here. So they plot in this happens in a three-dimensional space, but what's being plotted is just what happens on the specific edges of some specific zone of the crystal. So what you see here is the energies restricted to some specific paths, and what is called the Fermi level is what are, whenever somehow are the energies on what separates valence states to conduction states, which is this line here, which is when somehow the system is stable. And so these are the field states, somehow the electrons that do exactly are filling them, and these are the empty states, whenever something that we're solving the Hamiltonian, but we don't have particles there. And one way to think about these diagrams that I put is that each band, each line consists of composed of closely energy orbitals, but somehow they're bundled up very closely in just one single energy. But this one energy is not the energy of one electron, is the energy of 2 to the 22 electrons altogether. And they are somehow collapsed in one single somehow drawing. So whenever we have a valence band, we should think of 10 to the, so a lot of energy of all these electrons that are somehow being graphed as one density function. Good. So whenever we have these graphs of the energy with respect to some paths on the crystal that could be in position or in momenta, usually it's done in momenta, then these types of graphs appear, and they could be somehow interpreted differently, and somehow classifies the material. So if the energy levels cross the Fermi level, then this is the material conducts. So it's called a metal. If these energy levels cross the Fermi level in just one point, which is a band crossing, but they call it just 1 point or 2 points, it's called semi-metal. And whenever there is some gap between the valence states and the conduction states, depending how big is the gap, will be called a semiconductor, because somehow the electrons might jump. But if the gap is too big, it will be called an insulator. So these are materials that will not conduct. They will not conduct electricity. They will not conduct anything. So with this classification, we see that there's some sort of, it's not a continuous classification, but we see that how it goes. And if it's full of crossings, it's a metal. If the crossings are like this, these are a specific type of interesting materials. If the gap is small, then they might jump and be semiconductor, but if the gap is big, then they're called insulators. Good, that means that they don't conduct. These type of diagrams that the physicists might draw are like these ones, but of course, this is just a drawing of the energies. Somehow, whenever they do these computational calculations, one has not only the energy, one also has the eigenvector of the Hamiltonian, and the eigenvector is kept there, so one can somehow play with the eigenvector. But of course, what one sees graphically is these energy levels of the different energy bands of the crystal. Good. There are some principles in this energy crossing. So the first one is that it's called the von Neumann-Wigner repulsion principle, or it's an old, somehow beautiful result of von Neumann and Wigner, that the eigenvalues of the Hamiltonian, or the eigenvalues of these types of functional, will tend to separate. They will not cross. And if you might think that it's crossing, well, there's some sort of, you may think that there is some perturbation theory behind it that will somehow separate. So the energy levels will try to repulse each other. And unless there is some sort of symmetry in the equation, or in this crystal, let's say in the equation, that forces the crossing to be kept, that you cannot somehow do some sort of transversal intersection, and you cannot somehow separate the energy level. So they have to be degenerate. One way to think about this is that in the crossing, one has a non-trivial representation of a group symmetry, and therefore you may not be able to separate the states because they're somehow attached by the irreducible representation. So in these energy levels that would before, they tend to separate. They really, if you go looking closely, they separate unless some symmetry blocks them in. And these places where the energies are somehow collapse, or it's because there's a non-degenerate solution of the Hamiltonian, and is usually because the group symmetry is blocking it via an irreducible representation. And somehow these places where the energies somehow get together is where the important information lies. And there are two very important effects in these types, in materials, in metals. One is called the Hall effect, the other one is the spin Hall effect. The Hall effect is once one has a current in one direction and one puts a magnetic field perpendicular to it, the magnetic field will deflect the electrons to one direction, therefore somehow making a conduction in a direction transversal to the original direction of the electrons. So this is what is called the Hall effect. So namely, a magnetic field somehow defines a conductance in a direction perpendicular to the original one. The spin Hall effect is also same type of deflection, but on which spins with one polarization deflect to one side, and it spins with the other polarization deflect to the other, and then therefore one might get a spin current. So these are phenomena that appears on certain metals and some sense antiferro or some metals, and it depends on the magnetic field and the structure of the spins of the materials. Now there is a quantum version of it, recent, that is called the quantized. First one is the quantized anomalous Hall effect, and later on the quantized spin Hall effect, which is not due to an external magnetic field, but is due to an internal magnetization of the crystal. So the crystal might be ferromagnetic, namely it's already magnetized internally. You don't need an external magnetic field, or it may be an anti-ferromagnetic, namely that is the global magnetization is zero, but internally there is still some sort of magnetization that you might, that locally there is magnetization, although the whole integral is zero. So in this case, what happens is the same principle. So we have some current going in one direction, and due to the internal magnetization, it produces some current across it. So what is interesting about this is that it is quantized, and the quantization, or the number of the quantization, can be, well, it was detected some years ago in these works by the physicists. These experiments are carried out, and one can somehow detect the conductance, and the conductance with the conditions, appropriate conditions for the material, gets quantized, and this quantization is measured as the Chern class of some of the system behind it, and so this type of result led to the Nobel Prize in 2016. What is behind in the mathematical language is that what is called the anomalous Hall conductivity, which is precisely measuring this transversal current that is depending on the internal magnetization. And when one sees the formula, it is one can see that is related to precisely the integral of the very phase of the very connection or the very curvature. And then we know that once we integrate the very curvature, the curvature of the connection associated to the states of the system, then we know that this is quantized because this is the integral of the Chern class of the system. So what is behind in the anomalous Hall conductivity, in the formula of it, or the way it's calculated, is precisely the first Chern class of the system, of the whole energy system. And this is somehow what led to the quantization of the anomalous Hall conductance. But of course, there are many things that are underlying the system. We have the geometrical symmetries of the crystal, these translations, rotations, and all the ways they couple. We have the spin-orbit interaction. What we know is that if we take an electron and we go somehow around the nuclei, the spin gets reversed. And we also have some other symmetries. I call them meta-symmetries, but these are symmetries that are not somewhat in the crystal, but you may think that there are symmetries of the Hamiltonian. And these extra symmetries of the Hamiltonian play an important role in detecting the invariants. These symmetries are called time reversal symmetry, particle Hall symmetry, and some combination of the two that is called chiral symmetry. So the first one is the geometrical symmetries, that whenever we bring in the spin orbit coupling, we need to consider that we are not dealing with the rigid symmetries O3, but it's to connect the cover spin, the group pin n usually is called pin minus n, and so it's a two cover of the group On, and the group is not the one that is on the crystal per se, but you need to get this C2 extension of it, of course, because now we know that whenever we turn around 360 degrees, we recover a different sign or a different spin. And besides that, we also may have partial translations in our lattice that are somehow compounded with a rotation. You may have such type of symmetry, which is, it might be 180 degrees the rotation and then some partial translation. And that's an internal symmetry that we need to take into account. And these partial translations, once it is written into the coordinates of momenta, do a Fourier transform, then these partial translations, when acting on the space of states, they become a phase, but a phase that depends on the momenta coordinates. So, and this is another symmetries that play an important role in the classification somehow of these materials. This is coming from Bloch's theorem. So the three symmetries that are somewhat very important are whether the system preserves time, which is called time reversal. We should think that we simply flip time to minus t, so flip t to minus t. If somewhat the Hamiltonian is preserved by such a symmetry, namely that we change the momenta to minus momenta, and there are specific matrix associated to the time, and then we say that the Hamiltonian preserves the time reversal. What is important is that this symmetry is not unitary. That's very important. It's anti-unitary, the symmetry, and that somehow is what brings a lot of other types of topological invariants into the game. And this was already somehow explained by Wigner in the 1930s in his quantum theory book, that basically there are only two options for this anti-unitary symmetry. Namely, its square is 1, namely it's like a real symmetry, or its square is -1, and it's a quaternionic symmetry. Thinking of, we may relate to representations, and we have the real complex and quaternionic representation. Particle Hall symmetry is one on which somehow the Hamiltonian gets flipped with a minus sign. This is sometimes seen in the energy description, because the energy above the Fermi level and the energy below the Fermi level looks the same. It's just flipping. And this is not the case on which what I'm going to talk about. but it's called particle Hall symmetry because what is filled, you might just think that is equal to the one that is empty. On the conduction and the valence states look the same, and there is this symmetry. And the chiral symmetry is a combination of the two, and that one is unitary. For the time, I'm going to concentrate on time reversal.
Sorry,
yes.
the first anti-unitary, is it by any chance related to this charge conjugation that we also use in NCG? I mean, like for a spectral triples.
Yeah, charge conjugation is this, you may think is particle Hall symmetry because you change the charge to the minus charge.
The second one, I see. Yes. Okay, right.
Yeah. Sorry, I didn't. It just has different names on how you see it graphically, and so this was somehow done by different groups of people. This classification by two physicists, Altman-Zimbauer. But it somehow I'm just putting it in a snapshot. So depending on which type of symmetry or metasymmetry that the Hamiltonian has, either has time reversal or not, charge conjugation symmetry or not, and this chiral symmetry or not, then you have 10 options. And these 10 options that bring somehow endorse the eigenvectors of the Hamiltonian with a specific type of structure that we might think of Clifford algebras. And the classification on the letters is the one that is done by Altman-Zimbauer. But they, of course, relate directly to the homotopy groups of VU and the homotopy groups of VO. So we have two systems that could be thought as complex systems, which is A and A3. And then you see the Bott periodicity playing a role here of VU. And the other 8, whenever either time reversal is in or charge conjugation symmetry is in it, then we have a classification using the homotopy groups of VO. The case which 90% of the cases that in this condensed matter physics are discussed are the ones that are in the A2 level, namely we have time reversal symmetry preserved, and because we consider spin orbit coupling, then this time reversal symmetry square is -1, and that brings us to this 4th level. And the dimension here on top, since we are talking about crystals that are 3-dimensional, and we put the appropriate homotopy groups, then we see already that there is a Z2 invariant precisely from the homotopy groups of BO with the appropriate shift. And this invariant is the one that detects or not whether a material is a topological insulator. So what goes on the right is the different... Sorry?
Sorry, may I have a question?
Yes, I suppose.
Related to the previous one, in fact, since I'm a little bit confused, since physicists speak about this CPT symmetry, and as far as I know, C stands for charge conjugation and T stands for time reflection. So I'm a little bit confused whether this time reversal symmetry could be identified with this charge conjugation.
No, time reversal doesn't change the charge. Time reversal doesn't change the charge.
Okay. Yes, so these two are different, yes?
Yeah, time reversal is simply flipping the time around.
Mm-hmm.
Just simply put -T. And P
Yes,
and
so I think that this time reversal symmetry is not what appears naturally in NCG in the definition of real spectral triple. I think that in the definition of the real non-commutative geometry, this operator C is more like a charge conjugation, not like a time reversal symmetry. But maybe
I'm afraid I don't know how to somehow reply correctly what you're saying. I don't know exactly how it relates to other construction, which I suppose are similar. Perhaps it's just a translation problem. I'm dealing here with a very somehow simple case on this, which I have this Hamiltonian. No, the Hamiltonian I just put. and you may
Yeah, but
just simply shift the time
no, but I
around.
mean, it's very clear what happens. I mean, in NCG, the charge conjugation is the physicist charge conjugation. So it is the one which is called particle Hall symmetry. Yes.
Mhm.
You have it in the next page. If you go to your next page, yes, you have C, which is charge conjugation.
Yeah,
symmetry.
charge conjugation.
That's exactly the one which appears in noncommutative geometry. So this is very clear. Yeah.
Mhm. Okay, thank you.
So thank you. I was the one confusing everybody. So C is charge conjugation symmetry. But somehow this is not the one that I will consider. I will consider time reversal symmetry. Charge conjugation, as I said, will leave me a Hamiltonian that is that the energy levels will be equally on bottom and the top, and this is not the one that we're getting with this calculation of these materials. The point is that this number on the left, the 4, is what goes here on the real K-theory spectrum. If we want to know what is exactly the invariant that we need to calculate. So if we had charge conjugation, we would put 2 or 6, depending on whether C squared equals 1 or minus 1. So what we'll be dealing with is real K-theory 4 with respect to the point group symmetries or the groups that we had, and the point group. And here we have some sort of twisting of the K-theory group, which is depending on the non-symorphicity of the group, or depending also the information of the spin orbit coupling plays a role here, depending if we have partial translations. And since we are talking about these crystals in 3D, the dimension here is 3. So the topological invariant is KR4 equivariant twisted of the toroid to the 3. And I'm just trying to somehow give you all the detail, all the data that we need to put into account whenever we are in a specific level of this table. So good. So somehow this is the tenfold way associated to these symmetries. Now, just to give you an idea how we came to this, or the condensed matter is how they came to here. So so in the beginning of the 80s, David Towles was the one, his colleagues, to notice the quantization of the Hall conductance, by precisely noting that what they were calculating was precisely the very curvature of the connection associated to the two-dimensional system. And so this was the first somehow description of the quantization of this anomalous Hall effect. And the quantization, well, here with a picture of the genus, is giving you that is coming from in a quantized manner. Later, in the beginning of this century, it was also noticed that there are some materials which are insulating. Namely, there's a gap in the energy graph, whose nevertheless have a very nice conducting property on the surface, the boundary, either conducting or in the boundary on the hinges. But so these were denoted or were called topological insulators. Namely, they are insulating in the bulk, but once you construct a material with a surface, they are conductors on the surface, but not in the bulk. And these are called topological insulators. So somehow are insulating on the bulk, conducting on the surface. Topological because there is a topological invariant that was somehow constructed by Kane and Melle. And one of these materials is bismuth selenium. And one sees when one plots the energy that there is a gap. It's not big because it's less than 1 electron volt. But somehow this gap, even though it's telling you that it's insulating in the bulk, whenever the same picture is done on the surface, namely you cut the material on a specific surface and you carry out the whole computational calculation on the surface, then one sees that that it becomes conducting, because then you have a crossing of the energy goes from the valence to the conducting states. And the invariant could be either obtained using something that they call the Wilson loop, namely doing some sort of line integral across a loop and calculating precisely on all the states the winding number. Or it could be somehow seen by the somehow whether the quantized spin Hall conductance is not zero. And that these are different ways to know that a material becomes a topological insulator. And one way to see this is this little video that somehow these topological insulators will give you some sort of current where the spins in one direction going in one direction, the spins in the other direction go in the opposite. And later came extra classification of these materials, on which if the Fermi level crosses the energy graphs in specific ways, like something that is called here Weyl crossings, because the solution of the Hamiltonians was given already by Hermann Weyl, and then the physicists denoted these materials as Weyl semimetals with specific properties, conduction properties. And these types of crossings are of this type here that are easy to detect once you know the picture of the energy levels. And these crossings, although we know the Wigner-Poinomon repulsion principle, these energy crossings cannot be avoided, and the physicists call it topologically protected. The way they are topologically protected is because there are some group representations going around that don't allow you cannot somehow make it non-degenerate, the Hamiltonian, because the group doesn't let you do it. And of course, there is a lot of combinatorics behind, a lot of group theory behind, and there is a lot of work by the physicists of understanding what are the specific properties that these energy crossings give you physically. And then later came the 2016 Nobel Prize because of what we described at the beginning, which is the quantization of this anomalous Hall effect. And later came extra things, that the crossings of the energy might not only be point-wise crossing, but also loops. And the physicists call these objects topological nodal line semimetals, namely that not only could be points, but also paths. And so there is a lot of topological invariants that one can calculate on them. Point is that all these construction until then were based mostly on crystals that are not magnetic, namely that there is no internal magnetization. And the internal magnetization there are so many materials on which they are internally magnetized, either ferromagnetic or anti-ferromagnetic. And so for these materials, whenever that are anti-ferromagnetic, namely that the whole magnetization is zero, it was already brought into the game something that is called by some Axion electrodynamics, whenever you bring this topological term on the electromagnetic Lagrangian, which is one way to notice the topological thing is the second Chern class. And the way you see it here, the second Chern class, one also way to see it is that it's the component of the magnetic field that goes parallel to the electric field. And it turns out that this this component, if you have certain symmetries, then this number gets quantized. The two possible values is 0 and pi, and if one somehow calculates this number, this theta value here on the specific material, whenever you have an insulator, it turns out that whenever the insulator is non-trivial, namely is conducting on the surface, that already means that this value is different than 0, and the physicists call it pi. So there are two options, either 0 and it's normal, namely it's insulating in the inside and in the surface, or it's pi and it's an insulator in the inside but not on the surface. And one way to do it is by doping, by doing sandwiches of materials. Whenever you have some sort of Weyl point, if you just put some specific material with magnetization, you may open the gap, and by opening the gap, you make it insulator, but it may be that it has all internal properties that keeps them to be a topological insulator. And another way to see this term is basically the Chern-Simons term that I'm writing here, that knowing the Berry connection, theoretically, one can calculate it. And I say theoretically because computationally, it hasn't been so easy to do. It's too many terms to add, and so the error is not so easy to control, and it's not so easy to calculate. So therefore, even though one knows theoretically what is the invariant, the physicists are always thinking other ways to determine the invariant in such a way that they can calculate it. And so whenever you have materials that are internally magnetized, or the total the internal magnetization is not zero, and we know that that there's an insulator, namely there is a gap in the energy, and that we know that the integral of this Chern-Simons term is not zero. That means that we have some sort of symmetry that forces to be a specific value. These materials were denoted Axion insulators. So namely, what we had before, topological insulators were always with the Hamiltonian, always preserved time reversal by itself. But on magnetized materials, time reversal is not a symmetry. But what happens is that time reversal might be composed with another symmetry and preserves the Hamiltonian. And these other types of symmetries somehow force the Chern-Simons term to be either 0 or pi, and whenever it's pi, it was called that these materials would be called Axion insulators. And the symmetries that quantize this value of theta are not that many, are time reversal, inversion, namely change xyz by minus x minus y minus z, or combinations of time reversals with rotations. 180 rotations or 90 degrees rotations. There are not that many, but if a material has any of the symmetries, then the Chern-Simons term is quantized in two options, 0 or pi, and whenever that's the case, and it's an insulator, one needs to calculate it, and one knows the topological properties inside. Now, what this brings, and I'll put the whole picture, is that when one has a topological insulator, one wants to see what are the properties on a surface. Whenever you have time reversal, the time reversal is kept on the surface, and the time reversal forces, because of the symmetry, forces on the surface to be conducting. Namely, on the surface, there is always going to be an energy crossing at the Fermi level. And so for topological insulators, the surface is always a conductor. Meanwhile, in Axion insulators, could be anything. Could be that the surface is insulating or the surface is conducting. But whenever the surface is insulating, namely the gap is preserved, then there must be some sort of current somewhere, and the current is usually going on the hinges, on the one-dimensional objects, not in the bulk, not in the surface, but on the hinges. One of these materials that has been calculated experimentally is the magnesium, in English, bismuth, tellurium. The problem is that there are groups of people that have done it. In a group of people gets a gap in the surface, but another group of people does it and gets not a gap on the surface. So it's not completely clear exactly whether the surfaces are metallic or not, because of course depends on when you carry out an experiment, you don't have exactly the crossings. The gap might be too small. So it's still somewhat undecided in this case whether it's conducting or not on the surfaces. But there are some types of material that are pretty somehow good to be fit on these types of Axion insulators. One of those are the pyrochlore materials, and because they come with a specific magnetization that is called in physics all in, all out. You may think of a tetrahedra, and then some tetrahedrons have magnetizations going inside, and the next ones are the tetrahedra coming, all of them coming outside. The total magnetization is zero, and this was proposed by Vanderbilt, who works at Rutgers, as a material that might be an Axion insulator. And he carried out something that is called a tight binding model, on which you just put information of the first neighbors and the second neighbors, and you just numerically try to solve the Hamiltonian. And in this case, depending on the numbers that you put on the Hamiltonian, there are many phases, but some of them are precisely of the Axion insulator type. And this might be detected once one does the computation. There is a gap here that you can see in this this figure, and this gap gives a signal of the spin Hall conductance, and that's somehow a signal that the material might be conducting on surfaces or on hinges. And another way to do it is to find out what are the energy of the eigenvalues of the Hamiltonian on the surface. And whenever we see this Axion insulator detected by Vanderbilt, there is a gap. So, and the way to construct this is one does layers of this material, trying to construct a thin surface. And computationally, it was detected that already by the 8th layer, one gets a quantized value of the conductance, anomalous Hall conductance on the surface. Again, this is the material. The Neptunium bismuth is one of these examples that we carry out the calculation. I'll give you somehow the whole graphs. Again, these are the energies. There is some gap, small gap, and then the signal of spin Hall conductance. And these plus minus signs here is a way that was already carried out by Fu, Kane, and Nelly some years ago to detect whenever a material is an Axion insulator. That means that you have an extra symmetry, which is inversion. The inversion leaves 8 fixed points in the tori, and on those fixed points, you may calculate the eigenvalues of this inversion operator. And depending on these eigenvalues, you may detect whether you have or you don't have the topological invariant. And there's another way to detect whether a material is an Axion insulator or not. And in this condensed matter physics, when there's many ways to, they always like to have many ways to see the same phenomena. And another way is to somehow do a model, a local model of 4 bands on which one puts a specific Hamiltonian and one solves it computationally. And one sees that even though there are 4 bands and these are somewhat the energies, there is some flipping of something of orbital type. And the flipping of the orbital type is a way to detect the topological structure of the material, which is something that is here in different colors. It's a change of orbital type. Somehow the orbital type at the bottom is red, but suddenly it flips on the top. Just to finish, so here in this specific material, there is many surfaces. This is the vector perpendicular to the surface, and one sees that it's insulating. But whenever one takes a hinge, namely hinge here is just a path, it's a path given by this vector, then one sees that there is a conduction. Namely, this is a type of material on which it's insulating on the bulk, it's insulating on the surface, but it conducts on the hinges. And whenever one needs some 30 layers of the material in a sandwich way to get the anomalous Hall conductance. So the material has, of course, this sort of like structure locally, and what the arrows mean that the spins are circulating around the hinges with the direction that it has, the up in one direction and the down in the other direction, and it's giving you some sort of conduction, but not on the surface, but on the hinges. And there are some materials, very few of them, that has been detected to have this topological insulator property. And they're looking for more, because depending on how good they are at finding one, they might be able to build them on the lab. But I just want to finish to give this slide that I was just building up today to somewhat give you a hint of what is the topological invariant here that is underlying all this structure. And so what we take is a symmetry that is a rotation of 180 degrees and time reversal. It's a composition of these 2 things. And we might take a simple model as a 3-dimensional sphere, which you think that we have the space, which is a 3-dimensional tori, but we just collapse 5 boundaries into a point and we end up having a sphere. So the sphere has the 3 coordinates of momenta, and we just put an extra just to get a 3-dimensional sphere. When we see what happens with rotation around the z-axis, so this is a rotation of 180 degrees, so it flips the sign of kx and ky, but then time reversal flips the signs of all of them, and so this is the symmetry. If you take a look at what is this, this is a 3-dimensional sphere on which one of the variables gets flipped. If we see what is the square of the operator, the 180 degrees twice, because we have the spin orbit interaction, it becomes a -1. Time reversal square is also -1. Both coupled gives you a 1. So then the operator becomes like a real operator, not a quaternionic. Then one can construct a local model of what could be a 2-band model for the system, for the topological bundle around it, and one sees that the topological invariant is given by the real K-theory groups of this type of a sphere, namely two dimensions are being kept positive and 1 dimension is being flipped. And using the results of Atiyah, it's easy to calculate that this invariant is a Z2 invariant. But on the other hand, the same invariant, because the second Chern class is 0, because we only are living in the 3-dimensional space, the Chern-Simons invariant will in this case be the same as this K-theory invariant that is calculated on the left. Is the same as the secondary cohomology class constructed by Chern and Simon. So what to bundle everything up, there are these insulators, materials who do not conduct in the bulk. Whenever the crystal has a symmetry that is anti-unitary, namely could be T, time reversal only, or a composition of rotations with time reversal, the Chern-Simons term detects already the topological insulator property of the material. Namely, if it's not 0, then it's known that it will conduct somehow either on the surfaces or on the hinges. And now this term comes from, as I said, the topological term on the Lagrangian, but it could also be detected in several other ways if one knows the symmetries of the crystal, and one of them is knowing this K-theory invariant that appears here. There are somehow more structure behind all these K-theory calculations, and the idea is to organize all this information in such a way that that in condensed matter physics is clear which invariant does what and which invariant is equivalent to which other one, and this is somehow what has been done by several groups of people nowadays at the classification of crystals and magnetic crystals, which is one wants to deliver a table of what are all the topological invariants that are there, how do I calculate them, which information gives me which one, and then I can split the materials into different classifications depending on the topological invariants that they have. So the Axion insulators ones are, as I said, to finish, magnetized crystals internally, who do not conduct on the bulk, do not conduct in the interior, but which have specific conducting properties on the boundary or on the hinges. To finish, I apologize if it does all come as many things together. As I said, I'm not a condensed matter physicist. I'll try to do my best by bringing the topology I know, but I know that there are many loose ends in what I said, many things that are not completely clearly written, but I wanted to give you an idea of how one, what are these invariants written in a specific way that one can go and try to calculate them. So thank you very much for listening to me. Thanks you. Adam, please.
I was only tapping
very
my
much
hands
for your
virtually,
talk.
but nevertheless, I had a question.
Yep, sure.
So how this theory applies to the quasi-crystals, where the structure is no longer periodic, but in some sense almost periodic?
So, Adam, please, could you repeat it? I didn't hear because there was some noise. But what with periodic?
So how these methods apply to the case of quasi-crystals, where the structure is somehow not periodic, but almost periodic?
I just don't know. I don't if these methods are applied. I don't know, because I haven't seen what are the quasi-crystals, so I haven't. The methods at the end is if you manage to get some eigenvectors that bundle up into something that you might call a vector bundle, then these methods apply. But I don't know if that's what you were getting at the end when you solve the Hamiltonian. And if it's some sort of a well, here is compact because it's just a tori, but doesn't have to be compact. You just put all these eigenvectors together. If there is a gap, then you know that there is a vector bundle around that is complex because your solutions are complex valued. And depending on the symmetries, you put more extra structure, real bundles or quaternionic bundles, and then you put the groups, and then you might calculate the topological invariance of the vector bundle. Which, however you want to do it, with Chern classes, with Steeple-Whitney classes. The interesting fact is that these characteristic classes tell you some physics. But if you have such a setup, I believe you can just do it as long as you have a vector bundle.
But I mean, so in regard to Adam's question, I believe if you're dealing with quasi-crystals, then that's where instead of torus, you will have a non-commutative algebra. And all this technology carries, thanks to non-commutative geometry, I mean, non-commutative differential geometry and all these things exist. I think that's what Belisard did also some time ago. So, yeah, so right. Cyclic cohomology, now it's instead of Doran cohomology, you use cyclic cohomology. That's inevitable almost, yeah.
Wow, brilliant. Thank you.
Good point.
Yeah. But I had one question myself. I mean, I have a feeling I read or maybe saw somewhere that instead of Schrödinger equations, sometimes they use Dirac equations for these things. Is that correct? Is that the right? For the Hamiltonians, they use some relativistic equations.
Some relativistic terms sometimes, but in these ones, no.
I see. I mean, especially because you mentioned Weil metals. I mean, these are like the wave function for those things satisfy Weil equation, which is.
Yeah, so it looks like Weil's equation. You're right. So, but this is somehow local description of the Hamiltonian. It's not that the Hamiltonian is the Dirac equation. It's that locally it looks like Weil's equation. And then you use the solution to locally see what are this information.
Right. I see. Yeah. Yeah. Well, that's.
No, thanks for all. When Guillermo asked me to give a physics type of lecture, I knew I was going to stumble. So
can one say this effect in graphene?
You may blame me.
So and I did stumble. So.
No, I mean it was very physical for me actually.
So Bernardo, we have a question in the chat. Could you actually?
Oh, I see. Sorry. Just I don't. Where is the chat? Where is the chat? Where is the chat? Where is the chat? How do I see the chat? Chat. Okay. Is there an analog of the Aharonov bomb effect possible? Well, in this case, yes. One way that one description that the people in condensed matter physics work is that whenever we have crossings of the Hamiltonian, we can measure its Chern number around it, and then one can also graph or define the Berry curvature geometrically. So one can carry out the whole Berry curvature geometrically as a vector in the three-dimensional space, and then whenever we have crossings of the energies, we get some singularities, but not some singularities of the vector field, and those points could be thought of. It's not. Yeah, those points could be thought as points that are generating these vector fields, like sources, and so one might think that magnetic monopoles are these objects there. But this is just a copy of an argument, because they're not somehow physically anything, but they behave like, of course, because it's just there are just line bundles around it. They behave like magnetic monopoles, and so this Harmon bomb effect could be brought into the game, because exactly we have some sort of monopoles, but somehow we're just doing too many similarities. But it's not like precisely this Harmon bomb. But of course there are phases around it, and we measure them with the Chern classes, and the Chern classes precisely that gives this quantum Hall effect, precisely that. So that way we see some Harmon bomb. We're measuring around, and the particles rotate around, they spin up, spin down, and the way to measure it is going around and calculate the integral.
Therefore, earlier a question was given on quasi-periodic situation. If there is a quasi-periodicity, would there not be a fractional quantum Hall effect? Because it is not exactly periodic, it is quasi-periodic. That means there may be other solutions that are possible due to the quasi-periodicity.
And I suppose the experts on the audience know more than me about the questions you're asking. But I suppose you're right that there are other, because of the possibility you may get some sort of different phases.
That's what I mean. You can probably have different phases because it's not exactly periodic, but it is quasi-periodic.
It might be. You're right. But I don't know much about quasi-crystals.
Thank you. Very interesting talk. Appreciate that.
Thank you. Anyway, thank you very much. And I'm sorry for being late. I lost the link. I didn't know how to get it. So thank you for having me.
So are there any questions or comments? So,
yes. Can you hear me?
Yeah, we can hear you.
Wondering.
Please.
I was wondering if it's easy to see in the example of the Axion insulator that the Chern-Simons invariant takes values in Z-mod 2.
Yeah, the reason is because you apply time reversal, and then at applying time reversal, then you just see how the factors change, and since time reversal is a symmetry, you get a minus sign.
But wait, didn't you say the time reversal was not a symmetry? But
sorry,
time reversal.
You're right. I apologize. Time reversal reverses the sign. Now, time reversal is not a symmetry, but a rotation doesn't do anything to the theta invariant. So rotation doesn't do anything. Theta reverses the angle, and so the only possible is 0 or pi. Because these things don't change anything, because it's an integral, no? Since it's an integral, you may rotate, it doesn't change.
Okay, yeah.
Somehow this is the way they got it very easily, no? Because of the preservation of this anti-unitary symmetry, then they know it's 0 or pi. And then it's just a matter of calculating it. So it's a C2 invariant, Luke.
Yeah, okay, that makes sense.
So any more questions or comments? So
I have one more question.
Please. Yes, sure.
Would this type of effect be possible in graphene? Graphene can sometimes be treated as a massless Dirac equation problem, and which can be reduced to an equation analogous to the Schrödinger equation. And the question is whether one can observe.
Yeah, the thing is that graphene is two-dimensional, and this is a three-dimensional effect. the question could be, if I stack graphenes around,
Yeah.
then you might get something that they call it 3D churn insulator, but it hasn't been easy to somehow to do it that way. You know, you see, this is from the bulk coming to the boundary, and the other way is let's construct a three-dimensional material by stacking things. But somehow the symmetries have to be treated differently. But this is another way they can do it. But I don't see with graphene has been carried out that is an Axion insulator. I don't think so. No.
Okay.
Okay, so let's thank our speaker again for.
Thank you very much. Thank you very much. Thank you for having me.
Thank you.